At any given moment, about 1,800 thunderstorms are in progress somewhere on the globe. New observations by NASA's Fermi Gamma Ray Space Telescope show that thunderstorms make antimatter. The process starts with a terrestrial gamma ray flash, or TGF, an intense pulse of gamma rays originating from thunderstorms. On December 14, 2009, as Fermi passed over Egypt, it spotted a TGF produced by a thunderstorm in Zambia. The TGF was over the spacecraft's horizon, where Fermi couldn't see it. So how could Fermi have detected it? Scientists believe that the TGF process begins in a thunderstorm's intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultra-fast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays. The spacecraft has observed this phenomenon on at least 4 other occasions. So the next time lightning flashes and thunder roars, remember, you may be witnessing antimatter in the making.
Satellite, you're thinking something the size of a car or bigger. It's the size of a loaf of bread, and that's our satellite. There's been some evidence that lightning produces gamma rays, and this is really the first satellite that's going to go out and investigate if and how and where and everything associated with gamma rays coming from lightning. There's been evidence, and others have seen this, but again, there's never been a satellite dedicated looking down at Earth for these terrestrial gamma ray bursts.
Convective storms hold an extraordinary surprise. Under just the right conditions, they fire off some of the highest energy light naturally found on Earth, terrestrial gamma ray flashes, or TGFs. Rising and falling snow and ice particles repeatedly collide, filling the cloud with electrical charge. Once the electric field is strong enough, a current flows and a lightning flash occurs. The flash produces an abrupt reconfiguration of the electric field. In some cases, a surge of electrons rushes toward the upper part of the storm at speeds nearly as fast as light. When deflected by air molecules, these accelerated electrons give off gamma rays, producing a TGF. Data from NASA's Fermi Gamma Ray Space Telescope suggest more than 1,000 TGFs occur each day all over the globe. For the first time, improved data link dozens of TGFs to specific tropical weather systems. Tropical storms far from land tend to generate less frequent lightning. Nevertheless, observations show they are surprisingly prolific producers of TGFs. Tropical storm Manuel made landfall just shy of hurricane strength. As it rapidly weakened, it produced 2 TGFs within 24 hours. More typically, TGFs are associated with the strengthening phase of a storm. As Typhoon Bolivan rapidly developed in 2012, thunderstorms nearly 500 miles from its center launched a TGF with 4 distinct pulses. So far, the record holder for TGFs is the rapidly strengthening tropical wave that later gave birth to Hurricane Julio. It produced 4 TGFs within 100 minutes. A 5th followed the next day, with nothing further. What scientists learned so far is that weaker tropical storms are capable of producing more TGFs, and those events can arise anywhere in the storm. For stronger storms, like hurricanes and typhoons, TGFs are more common in the outer rain bands, which host the highest lightning flash rates in these storms. The findings provide new insights into the relationship between storm intensity, lightning frequency, and TGFs. This adds another important piece to the puzzle of our understanding of TGFs and how they are created in thunderstorms, the most powerful natural particle accelerators on planet Earth.
Using global lightning location networks, scientists can determine a TGF position more accurately than with Fermi data alone. 24 localized TGFs occurred within areas covered by next-generation weather radar systems. This gives scientists the opportunity to begin studying the kinds of storms that produce TGFs. These slices of radar data capture different types of storms encompassing a wide range of updraft strengths. Even the weakest of them produced a TGF. Another finding, TGFs seem to occur in the same altitude range, between 7 and 9 miles high. Lightning can form at much lower altitudes, so there's every reason to think TGFs can too. But gamma rays from TGFs occurring deeper in the atmosphere are greatly weakened. They're too dim for Fermi to detect, which probably means the satellite is undercounting them. TGFs may be far more common than we think. With this knowledge, scientists can design experiments to track storms and study how TGFs relate to their strength in evolution. This will give us an even better understanding of planet Earth's most powerful natural particle accelerator. New research combines Fermi detections with ground-based radar and lightning location data